Hello, my name is Emmanuel Machado, and together with Luis Carlos Goes, we will present the work related to the improvement of the SHEFE simulator level flight performance model using flight test data. We will attend the following summary. We will make an introduction with the history of the project and the objective of this work. In the materials and methods sections, we will describe the methods and how data collection and flight tests were performed. In results and discussion, we will show the results obtained in the level flight power model, the graphics obtained with the engine parameters, and the positions of the flight control through the entire flight. Finally, we will present the conclusions with the most significant contributions of this work. Introduction. In Brazil, the largest helicopter flight simulator developed by the national industry is at the Army Aviation Command in Taubaté, São Paulo. The Fennec helicopter simulator SHEFE was developed by Spectra Technology in partnership with Brazilian Army. It's a full flight simulator. At SHEFE, it is possible to carry out basic, advanced, and mission training in specific locations and with special equipment, such as the use of night vision goggles. The simulator was built on top of a mobile platform, and inside the dome there is a replica of the flight deck of a Fennec helicopter and all embedded system, visual, audio system. To better represent the behavior of an aircraft, a simulator needs to have mathematical models that reproduce its flight characteristics. The flight models included in SHEFE were developed by Cruz in 2009. This work aims to increase the flight envelope available in the simulator's flight calculation model to improve the fidelity of the currently existing model. Materials and methods. The knowledge of the power required for level flight of the helicopter in all its range of speed and weight is important to determining the performance characteristics of the aircraft model. The lift coefficient of the aircraft is proportional to the level of power needed for the flight, and it's a function of several unchanging physical parameters such as rotor disk area, gravity, acceleration, air density at sea level, and rotor's radius. The only parameters capable of being changed are mass as function of fuel consumption and sigma, which is the ratio between pressure and temperature. To determine the power parameters of this type of flight, the method of maintaining reduced mass for different forward flight speeds was used. Fuel consumption changes the total weight of the aircraft, and altitude adjustment is necessary to maintain the same reduced mass ratio and consequently the same lift coefficients. An integration of the level flight data with the hover flight data outside ground effect was performed. Using the algorithm presented by Cruz in 2009, the algorithm calculates the reduction in induced power as a function of the decrease in induced speed by the main rotor with the flight ahead. Measures to collect the flight data needed for the analysis. The helicopter was instrumented. Parameters was collected like atmospheric from the engine, of fuel system, flight controls, aircraft attitude angles. All data was stored by spectral recording system with sampling frequency of 100 Hz. Before the flights, all equipment were tested and calibrated. Test flights. All flights were performed without external equipment installation like ammunition to the aircraft and with closed doors. This is in order not to modify the aerodynamics characteristics of the helicopter. The heating system and the sand filter were turned off so as not to consume power from the engine. The reduced mass parameters were established to cover a larger area of the flight envelope, divided into 5 values, the minimum and maximum limits possible to be reached in the test region. During flight, as fuel was consumed, the new adjustments calculations were performed to define the new altitude to be reached to maintain the reduced mass ratio with a maximum variation of 2%. The test points were performed at speeds between 40 knots and the maximum horizontal speed, VH. The 40 knot speed was determined to be the lowest possible speed for reliable reading on the aircraft speed indicator. VH was determined from level flight at continuous maximum power. Data was recorded for approximately 60 seconds. For level flight, the tolerance allowed at each test point were 1 knot for the indicated speed and 20 feet for the indicated altitude. Results and discussions. Here we can see in the graph on the left the data obtained in flight parameterized by the reduced mass. We have torque and velocity. The curves were fitted in second-degree equations using the least square method. The curves parameters are described in the table above. Using the data from an outside ground effect hoverflight test, together with the algorithm used by Cruz, it was possible to generate the complete level flight power model of the helicopter from 0 knots to VH. All the parameters of these curves are shown in the table above. Engine data is important for representing aircraft behavior and for performance calculations. The graphs presented show the rotation of the gas turbine and G in percentage in relation to the speed of the helicopter. A similar graph relates the turbine combustion changer exit temperature T4. Both have the same behavior of decreasing their values for speeds between 50 and 70 knots, increasing for maximum forward speed. The third graph shows the correlation between T4 and G values. The graph was assembled with all data collected in flight and a curve fit performance use a least square method. Here we have the flight command variations. The first graph shows the longitudinal cyclic command position with increasing speed. The result confirms that the flight command is placed forward with increasing speed. The lateral cyclic command variation graph shows that the forward speed increase, the lateral command shifts for the left. The collective command has a behavior equivalent to the power curve, since this command controls the power used by the helicopter. Finally, the pedal command is present, showing that intermediate speeds there is a displacement of the left pedal, and for other speeds there is a pedal movement to the right to compensate the aerodynamic effects of the aircraft. The complete level flight characteristics of the Fennec aircraft were investigated and tested for implementation in SHEFE helicopter simulator. The most significant contributions are taking advantage of all flights performance. A complete level flight model of the Fennec helicopter was developed to be implemented in the SHEFE simulator include transmission and engine performance data and flight command positions. It was possible to insert overflight data to complement the curves obtained in level test flights. Adopting the new mathematical model developed with will better represent the simulator in relation to the simulated aircraft model, enabling more realistic training for the pilots. It was determined the characteristic of level flight speed for each associated curve. Thank you very much.